Hello, everyone. In this section of electronics, we will introduce DC circuit analysis for bipolar junction transistors, or BJTs. This section focuses on case 4. In the previous section, we finished the case 3 BJT circuit analysis. Now we introduce the most commonly used DC biasing method, as shown in the circuit. This circuit can be viewed as a variation of case 3. All three BJT terminals are connected through resistors, and the base voltage is determined by two bias sources, VBB1 and negative VBB2, together with two resistors, RB1 and RB2. We can first divide this case 4 circuit into two parts. The two parts are the base bias network that determines the base voltage, VB. This network includes VBB1, negative VBB2, RB1, and RB2. The other part is the BJT circuit outside the base terminal, which has the same form as case 1. In other words, we use VB as the boundary and split the circuit into these two parts. The base bias network can be treated as a voltage source, so we can convert it independently into a Thevenin equivalent circuit. The Thevenin voltage, VBB, is the open circuit voltage of the bias network. It is obtained by voltage division. The total voltage, VBB1 plus VBB2, is multiplied by RB2 divided by the sum of RB1 and RB2, then plus negative VBB2. This gives the open circuit voltage, VBB. For the equivalent resistance, we could use the short circuit current method, but there is a faster method. As introduced in the amplifier equivalent circuit chapter, we set the independent voltage sources to 0 and look back into the output terminal. After setting VBB1 and VBB2 to 0 volts, the resistance seen from the output is RB1 in parallel with RB2. This is the Thevenin resistance RB. After converting the bias network into its Thevenin equivalent and combining it back with the BJT circuit, the resulting circuit has the same structure as case 3. Then we can analyze it using the case 3 method to find the voltage and current at each of the three BJT terminals. Now let us look at an example of a case 4 BJT circuit. The bias voltages and resistor values are labeled in the circuit. The first step is to convert the base bias network into its Thevenin equivalent circuit. From the voltage divider, the Thevenin voltage VBB equals 200 kiloohms divided by 200 kiloohms plus 200 kiloohms multiplied by 16 volts plus 0 volts. Therefore, VBB equals 8 volts. The Thevenin resistance RB is 200 kiloohms in parallel with 200 kiloohms, so it equals 100 kiloohms. After this conversion, the circuit becomes the same case 3 circuit that we practiced earlier. We can then use the previous method to calculate the three terminal voltages and currents of the BJT. Next, let us look at a more advanced example, a cascaded BJT circuit. This circuit consists of a case 4 circuit using Q1, an NPN BJT, cascaded with a case 1 circuit using Q2, a PNP BJT. Since Q1 is a case 4 circuit, we first need to convert its bias network into a Thevenin equivalent circuit. After converting the bias network of Q1 into its Thevenin equivalent, we obtain the circuit shown on the right. The Thevenin voltage VBB equals 50 kiloohms divided by 100 kiloohms plus 50 kiloohms multiplied by 15 volts. Therefore, VBB equals 5 volts. The equivalent resistance RB is 100 kiloohms in parallel with 50 kiloohms, which equals about 33.33 kiloohms. After this conversion, the cascaded circuit becomes a case 3 circuit connected to a case 1 circuit. We first analyze the first stage case 3 circuit. Assume that all BJTs in the circuit operate in active mode. Therefore, we can use the resistance reflection rule to find the base current IB1. IB1 equals VBB minus VBE1, divided by the sum of RB plus 1 plus beta times RE1. Substituting the numbers, the numerator is 5 volts minus 0.7 volts, and the denominator is 33.33 kiloohms plus 101 times 3 kiloohms. The result is approximately 0.0128 milliamps. After finding IB1, we can calculate the base voltage of Q1. VB1 equals VBB minus IB1 times RB, which is 5 volts minus 0.0128 milliamps times 33.33 kiloohms. This gives about 4.57 volts. Then the emitter voltage of Q1 is VE1 equals VB1 minus VBE1, so it is 4.57 volts minus 0.7 volts, or about 3.87 volts. Next, using the current relationship of the three BJT terminals, IE1 equals 1 plus beta times IB1. With beta equal to 100, this is 101 times 0.0128 milliamps, or about 1.29 milliamps. Then IC1 equals IE1 minus IB1, so it is approximately 1.28 milliamps. The collector current of Q1 is supplied through RC1 and is also affected by the base current of Q2. Since a BJT base current is usually much smaller than its collector current, we first assume that IB2 is much smaller than IC1. With the approximation IB2 much less than IC1, the current through RC1 can be approximated as IC1, about 1.28 milliamps. Therefore, VC1 equals VCC minus IRC1 times RC1. This is 15 volts minus 1.28 milliamps times 5 kiloohms, giving about 8.6 volts. After obtaining the three terminal voltages and currents of Q1, we check VCE1. VCE1 equals VC1 minus VE1, which is 8.6 volts minus 3.87 volts, or about 5.1 volts. Since this is greater than 0.3 volts, the active mode assumption for Q1 is valid. After analyzing the first stage Q1 circuit, we have the three terminal voltages and currents of the NPN BJT. IB1 is 0.0128 milliamps, VB1 is 4.57 volts, VE1 is 3.87 volts, VC1 is 8.6 volts, IE1 is 1.29 milliamps, and IC1 is 1.28 milliamps. During this calculation, we assumed that IB2 is much smaller than IC1. In the cascaded circuit, the collector voltage of Q1 is shorted to the base voltage of Q2. Therefore, VC1 equals VB2, which is 8.6 volts. Since Q2 is a PNP BJT, its emitter voltage is VE2 equals VB2 plus VEB2. Therefore, VE2 equals 8.6 volts plus 0.7 volts, or 9.3 volts. After obtaining VE2, we can immediately calculate IE2. It equals 15 volts minus VE2 divided by RE2. That is 15 volts minus 9.3 volts divided by 2 kiloohms, giving 2.85 milliamps. Then, using IC equals alpha times IE, we get IC2 equals alpha times IE2, which is 0.99 times 2.85 milliamps, or about 2.8215 milliamps. After finding IC2, we can calculate VC2. VC2 equals IC2 times RC2, which is 2.8215 milliamps times 2.7 kiloohms, or about 7.62 volts. We can also use IB equals IE divided by 1 plus beta to find IB2, so IB2 is approximately 0.0282 milliamps. Now the three terminal voltages and currents of Q2 are known. Checking VEC2, we get VE2 minus VC2, which is 9.3 volts minus 7.62 volts, or about 1.7 volts. Since this is greater than 0.3 volts, the active mode assumption for Q2 is also valid. Now let us feed this result back to the first stage analysis. In the first stage calculation, we assumed IB2 was much smaller than IC1, so we ignored the effect of IB2 when calculating IRC1. Now we substitute the calculated value of IB2 back into the first stage current. IRC1 equals IC1 minus IB2, which is 1.28 milliamps minus 0.0282 milliamps, or about 1.252 milliamps. Using the corrected value of IRC1 after one iteration, we can calculate the corrected VC1. VC1 equals VCC minus IRC1 times RC1. This is 15 volts minus 1.252 milliamps times 5 kiloohms, giving 8.74 volts. Since VC1 is shorted to VB2, this also updates the base voltage of Q2. Therefore, the corrected emitter voltage of Q2 is VE2 equals VB2 plus VEB2, which is 8.74 volts plus 0.7 volts, or 9.44 volts. Then the corrected IE2 is 15 volts minus VE2 divided by RE2. This gives 15 volts minus 9.44 volts divided by 2 kiloohms, or 2.78 milliamps. Next, IC2 equals alpha times IE2, so it is 0.99 times 2.78 milliamps, or about 2.752 milliamps. We then update VC2 as IC2 times RC2, giving about 7.43 volts. Also, IB2 equals IE2 divided by 1 plus beta, so IB2 is about 2.78 milliamps divided by 101, or 0.0275 milliamps. Finally, we compare the value of IB2 after one iteration with the value obtained before iteration, when the effect of IB2 was ignored in calculating IRC1. The difference is only about 2.5%. In other words, using the approximation that IB2 is much smaller than IC1 gives a quick result for the whole circuit, and the error is not large. Lastly, we introduce a circuit where an NPN BJT and a PNP BJT are stacked together. As shown in the circuit, the emitters of Q1 and Q2 are shorted together. Their collectors are connected to DC voltage supplies, and their base terminals are also shorted together. Because the base nodes are shorted and the emitter nodes are also shorted, the base emitter voltage of Q1 and the emitter base voltage of Q2 have opposite polarities. Therefore, Q1 and Q2 cannot turn on at the same time. If Q1 turns on, VBE1 is about 0.7 volts, which makes VEB2 negative and turns Q2 off. Conversely, if Q2 turns on, VEB2 is about 0.7 volts, which makes VBE1 negative and turns Q1 off. Let us first assume that Q1 turns on and operates in active mode. Then VBE1 can be approximated as 0.7 volts. At the same time, VEB2 becomes negative 0.7 volts, so Q2 is in cutoff and can be treated as an open circuit. As usual, we start from the base to emitter current path of Q1. Because both the base and emitter of Q1 are connected through resistors, we can use the resistance reflection rule to quickly find IB1. IB1 equals the total available voltage, VBB minus VBE1, divided by the equivalent resistance reflected to the base side. The denominator is RB plus 1 plus beta times RE1. Numerically, this is 5 volts minus 0.7 volts divided by 10 kiloohms plus 101 times 1 kiloohm. The result is about 0.0387 milliamps. After finding IB1, we calculate VB1 as VBB minus IB1 times RB1, which gives about 4.613 volts. After finding VB1, we obtain VE1 by subtracting VBE1. Therefore, VE1 equals 4.613 volts minus 0.7 volts, or 3.913 volts. From IB1, we calculate IE1 as 1 plus beta times IB1, giving about 3.9087 milliamps. The collector current is IC1 equals IE1 minus IB1, which is about 3.87 milliamps. Finally, we check VCE1. It equals VC1 minus VE1, or 5 volts minus 3.913 volts, which is 1.087 volts. Since this is greater than 0.3 volts, the assumed state of Q1 is valid. But what if we assume that Q2 turns on instead? In that case, VEB2 would be 0.7 volts, and VBE1 would be negative 0.7 volts, so Q1 would be in cutoff and treated as an open circuit. We then analyze the base-to-emitter current path of Q2, again using the resistance reflection rule. The calculated base current is IB equals VEE2 minus VEB2 minus VBB divided by RB plus 1 plus beta times RE2. Substituting the numbers gives 0 volts minus 0.7 volts minus 5 volts divided by 10 kiloohms plus 101 times 1 kiloohm, which is about negative 0.051 milliamps. This negative current means the assumed current direction is opposite to the calculated result. In other words, the current would flow into the base terminal of Q2, which is inconsistent with the PN-PBJT operation mechanism. Therefore, the assumption that Q2 turns on is wrong, and Q2 does not conduct in this circuit. This concludes the Introduction to DC Circuit Analysis for Bipolar Junction Transistors, Case 4. Please look forward to the next lesson. See you next time. Bye-bye.